This is a short refresher lecture on solving recurrences. We're going to focus on the type of recurrences that arise in divide and conquer algorithms. A classical recurrence is that for merge sort. T of n equals 2 times T of n over 2 plus order n. To sort n numbers, we partition the list into the first n over 2 numbers and the last n over 2 numbers. We recursively sort those two sublists. That takes time 2 times T of n over 2, and then it takes us order n time to merge these two sorted lists together. As you probably know, this recurrence solves to order n log n. Let's look at some other recurrences that we've seen so far in divide and conquer examples. The naive algorithm for integer multiplication had the following recurrence: T of n equals 4 times T of n over 2 plus order n. And we claim that this solves to order n squared. We'll see why momentarily. Our improved algorithm for integer multiplication had 3 subproblems instead of 4 subproblems, so we had the following recurrence: T of n is at most 3 times T of n over 2 plus order n. And we claim that this solves to order n to the exponent log base 2 of 3. And recall this exponent is roughly 1.6. Now another recurrence which we saw in the median finding algorithm was T of n equals T of 3/4 n plus order n. And we claim that this recurrence solves to order n. Now let's go ahead and solve these recurrences. We'll start with this recurrence, the naive algorithm for integer multiplication. Then we'll look at this slightly more complicated example. And finally, we'll look at the general solution for these recurrences of this form. We're looking first at this recurrence, T of n equals 4 T of n over 2 plus order n. Let's start by getting rid of the big O notation. Order n means that there's some constant c, so that T of n is at most 4 times T of n over 2 plus Cn. So we replaced order n by at most Cn. We also have the base case. Let's say the base case is of size 1. Since the input is of size 1, it must solve in order 1 time. So we can replace that order 1 by a constant c. And notice we can use the same constant c for both of these by taking the max of these two constants and calling that c. Let's solve for T of n. So I simply restated the recurrence, though for convenience I rearranged the terms. So T of n is at most c times n plus 4 T of n over 2. Now let's replace T of n over 2 by this recurrence. So replace n by n over 2. So we get this term c times n again. Plus we get 4 times, and then let's replace T of n over 2 with this expression. So we get 4 times T of, and we're replacing n by n over 2, so we get n over 2 squared. And then for the last term, we're replacing n by n over 2, so instead of c times n, we get c times n over 2. Now let's rearrange this and collect similar terms. So we want to collect c times n with 4 times c times n over 2. So these have a common factor of c times n. This term is 1. This term is 4 over 2 times c times n. And then finally, the last term is 4 squared times t of n over 2 squared. Now let's repeat this process and replace t of n over 4 by this expression. Now we're replacing n by n over 2 squared. So the first term becomes 4t of n over 2 cubed. And the last term becomes c times n over 2 squared. Rearranging once again, so bringing this term over here. So we have T of n is at most c times n times the quantity 1 plus 4 halves plus 4 halves squared plus 4 cubed times T of n over 2 cubed. Notice we're starting to get a geometric series here. What we've seen so far is that for this recurrence, T of n equals 4 T of n over 2 plus order n. By substituting in 2 times, we get T of n is at most c times n times the quantity 1 plus 2 squared plus 4 cubed times T of n over 2 cubed. Now notice we're leaving this as 4 over 2 and 4 over 2 squared instead of 2 and 2 squared, so that we see the geometric series that's going to arise. And this illustrates how the geometric series that arises is related to the original recurrence. The 4 comes from here, and the 2 comes from this term. At this point, we see the pattern. So now suppose instead of substituting in 2 times, we did it I times. Well, to be precise, let's suppose we substitute in I minus 1 times. So this geometric series becomes 1 plus 4 halves squared, and so on, up to 4 halves to the I minus 1. And this last term becomes 4 to the I times T of n over 2 to the I. Now when do we stop? What I do we stop at? Well, we stop when we get to the base case, which is when this quantity is 1. And whether we stop at 1 or 100, it doesn't matter. So let I equals log base 2 of n. Then 2 to the I is n, so n over n is 1. So this quantity is 1. So substituting in I equal log base 2 of n, we get the following expression. Now let's try to simplify the terms here. First off, what is t of 1? T of 1 is at most c, so we can upper bound this by c. What is 4 to the log base 2n? Well, this is order n squared. C times n is order n. Now what about this geometric series? Now the key thing is that this geometric series is increasing. 4 over 2 is bigger than 1. It's 2. So the last term dominates. So this whole expression is dominated by order the last term. So this geometric series is on the order of 4 over 2 to the log base 2n. We can forget about the minus 1 because that's hidden in the big O notation, because that's just an extra factor of a half. Now let's simplify this quantity. The numerator is 4 to the log base 2n, which we said before is order n squared. The denominator is 2 to the log base 2n, which is of course n. So this quantity is order n. Plugging it in, we have order n times order n plus order n squared. So this is order n squared plus order n squared, which is order n squared. So this recurrence solves to order n squared. The key element of these recurrences is this geometric series that arises. So let's take a look at geometric series in general. Consider some positive constant alpha. In our previous example, alpha was 4 over 2. And we're looking at this geometric series. We're summing over j going from 0 to k of alpha to the j. Expanding this out, we have 1 plus alpha squared, and so on up to alpha to the j. Now, since we're solving our recurrences within big O notation, we don't need to solve this expression exactly. We simply need to solve it within constant factors. So that makes life much easier. Now, the key for a geometric series is to figure out which term dominates. Either the first term, the last term, or all terms are equal. The three cases are whether alpha is bigger than 1, equal to 1, or less than 1. Now, if alpha is bigger than 1, then each term is growing. So the last term is going to dominate. So the whole expression is going to be on the order of the last term. Conversely, if alpha is less than 1, then the terms are decreasing and the first term dominates. So the whole expression is on the order of the first term, so it's order 1. Finally, the middle case is if alpha equals 1. Then every term is exactly 1, and then the number of terms is k plus 1. So the whole thing is on the order of k. This first case, where alpha is bigger than 1, is what arises in the recurrence we just analyzed. In that case, alpha equals 2. And what we saw there was that the last term dominates. When we look at merge sort, then we'll have alpha equals 1. All of the terms will be the same, and we'll get an order log n from that. The final case is what arises in the example of the median finding algorithm. There, we'll have alpha equals 3/4. So the geometric series which arises will be on the order of 1. The final tool that we'll need is manipulating polynomials. What we saw in the previous example is that 4 raised to the power log base 2 of n is the same as n squared. Now that example is quite straightforward, but we're going to have other examples which arise, such as 3 raised to the power log base 2n. And we want to convert this into a polynomial, so we want to convert this into n to the c for some constant c. And we want to figure out what is this constant c. So let's see the basic recipe for converting this into a polynomial. The key is that the base of this log is 2. So I want to change this base from 3 to 2. Well, 3 is the same as 2 raised to the power log base 2 of 3. That's by the definition of log. So let's substitute this in to this expression. So we have 3 raised to the power log base 2n. And then we replace 3 by this expression. So we have 2 raised to the power log base 2 of 3 raised to the power log base 2 of n. Notice these exponents multiply. So this is the same as 2 raised to the power log base 2 of 3 times log base 2 of n. And we can rewrite this as 2 raised to the power log base 2 of n raised to the power log base 2 of 3. What we've done is just swap these exponents. Now look at this inner quantity. That's just n. So we have n raised to the power log base 2 of 3. So we see that this exponent, c, is log base 2 of 3. Now let's take a look at the following recurrence. T of n equals 3 t of n over 2 plus order n. This is the recurrence which arises in the more sophisticated integer multiplication algorithm. Just as before, rewriting this to eliminate the big O notation, we have t of n is at most c times n for this term, plus 3t of n over 2 for that term. Now substituting in as we did before, and repeating it I minus 1 times, we get the following recurrence. T of n is at most c times n times a quantity, 1 plus 3 halves plus 3 halves squared, and so on, up to 3 halves to the I minus 1, plus 3 to the I times t of n over 2 to the I. Notice that before we had a geometric series with base 4 over 2, and now we have a geometric series with base 3 over 2. And instead of 4 to the I, we get 3 to the I. This is because we replace this 4 with 3 here. Now once again, we're going to stop when we get to the base cases, which is when this is 1. So we're going to stop when I equals log base 2 of n. Why is it base 2? Because we have 2 to the I here. So if we would have had subproblems of size n over 3, then we would stop when we have log base 3n. Now plugging this in, we get the following expression. So we have t of n is at most c times n times the quantity 1 plus 3 halves, so on, up to 3 halves to the log base 2n minus 1, plus 3 to the log 2n times t of 1. T of 1 is at most c. C times n is order n. What about this geometric series? Well, the base is 3 halves, so it's an increasing geometric series. The last term dominates. We can forget about the minus 1. That's just an extra factor of 2/3. So this is on the order of 3 halves to the log base 2n. The numerator is 3 to the log base 2n. The denominator is 2 to the log base 2n. 2 to the log base 2n is n, so that cancels with this n. This order n cancels with this 1 over order n. So we get order 1 times order 3 to the log base 2n. And this term is also order 3 to the log base 2n. That's not a coincidence. This should be the last term of this geometric series, so they should be on the same order of magnitude. Finally, we want to manipulate this into a polynomial. And we just saw that this is on the order of n to the log base 2 of 3. Now let's look at a more general form of recurrences. So for positive constants a and b greater than 1, let's look at the recurrence t of n equals a t of n over b plus order n. Our previous two examples had b equals to 2, and we did the case where a equals 4 and a equals 3. Now the recurrence for the median finding algorithm has a equal to 1 and has b equal to 4/3. And merge sort has a equal to 2 and b equal to 2. Now when you expand this out, you get c times n from this order n times the following quantity, 1 plus a over b squared, and so on up to a over b, and then it's going to stop when we get to log base b of n. And the last term is going to be a raised to the power log base b of n times t of 1, which is order 1. Now the key is what happens for this geometric series. It depends on whether a over b is greater than 1, equal to 1, or less than 1. If a is bigger than b, then we get an increasing geometric series, and the last term dominates. If a equals to b, then we get a geometric series where every term is 1. If a is less than b, then we get a decreasing geometric series and the first term dominates. Let's do the easy case first. A less than b, so the first term dominates. So this geometric series is on the order of 1. So we get order 1 for this geometric series, get order n here, so the whole thing is going to be order n. So we get order n in this case. What happens when a equals to b? Then each of these terms is 1, so we get log n terms. So the geometric series is on the order of log n. So we have order n times order log n, so that's going to be order n log n. So in the case a equals to b, we get order n log n. That's for merge sort. Finally, what happens in the case when a is greater than b? Now the last term dominates. Notice the denominator here is b raised to the power log base b of n, which is n. So this term cancels this term. So the whole thing is on the order of a raised to the power log base b of n. Converting that into a polynomial, we get that this recurrence in the case a is greater than b is on the order of n raised to the power log base b of a. And of course, one can look at more general forms of recurrences, where here we have, instead of order n, we have order n raised to the power d, where d is a constant. This is commonly referred to as the master theorem, And you can look at your textbook for the form of the master theorem and the solution to the master theorem.